Today I'm going to talk about LeetCode question number 322, coin change. So you're given an array of coins representing coins of different denominations and an integer amount representing the total amount of money. Return the fewest number of coins you need to make up that amount. If that amount of money cannot be made up by any combination of the coins, return -1. You may assume that you have an infinite number of each kind of coin. So for here, this first example here, we have the coins of denomination 1, 2, and 5, and we need to total up to 11. And the fewest number of coins we can do that is using 2 5s and 1 1, so 3. And the second example here, we only have a coin of value 2, and we need to add up to 3, and that's impossible, so we return -1. And this last example, to get to amount 0, we need 0 coins, obviously. Okay, so how do we approach this? So you might, our first thought might have been to do it a greedy way. That is, get the largest amount, get the largest denomination that's still less than or equal to amount, and get as many large ones as possible. And whatever is left, then we can add that to our final results. So for example, here we want to total up to 11, and we have coins 1, 2, and 5, so we can take 5, and 11 minus 5 is equal to 6, so we have 6 left, so we take 5 again, okay, which minus 5 is equal to 1, and now we can take 1, so 1, and total of 3 here. But taking this greedy approach won't work, and I'll show you a counter example. So let's say we have 1, 3, 4, and 5, and we want to total up to 7. So if we took the greedy approach, we'd have 1 5 and then 2 1s. And the total amount of coins here is 3. But there's a better way with fewer number of coins, and that'd be 4 and 3. So we can see the greedy approach won't work. What we can do instead is a dynamic programming solution. How are we going to do that? Well, we're going to keep a dynamic programming array here. Okay. Let's just take this first example. So we want to total up to 11, and this dynamic programming array will be of size 12. So length of dp is going to be equal to 12, y12. Let me take the previous example here. Instead of 11, that's going to be a large array and too much to draw. So I'll take the previous example of 1, 3, 4, and 5, where total is equal to 7. So we're going to have a dp array of length dp is going to be equal to 8 and y8. Because first value is going to be 0, so amount is 0, we'll need 0 coins, and then all the other positions will represent, index 1 will represent the coin of amount 1, index 2 will represent coin amount 2, 3, etc. Index 2 will represent amount 2, index 3 will represent amount 3, etc. all the way to 7 here. And what we're going to do in this array is, so for each amount here in the array, we're going to calculate how many coins it will take to get to this coin amount. Okay. And why are we going to do that? Well, we're going to build up the solution here so that eventually when we get to say 7 here, we will know already how many coins it will take to get to this amount. So I'll walk through it. So for example here, we iterate through our coins array for of amount 1. Obviously we see only one coin will total to 1, so it'll be 1 here. And for 2, we iterate through the array here, and we find all values that are less than or equal to 2. So in this case it'd be 1. Okay, and then we have 1 left, but we already calculated 1 right here, so we can actually use this value. Okay, so then what we have here is 1 plus dp of, or let me be, so dp of 1 plus 1, which is going to be 2. So that's what's going to be here. And for 3, and then we iterate through the rest of the array here. They're all greater than 2, so we don't count them. And for 3, what are we going to do here? So we iterate through the array, find all values that are less than or equal to 3. So 3 minus 1, turns out 3 minus 1 is equal to 2. And we already calculated the total number of coins, the smallest number of coins to take to get to 2. So we're going to take that value here, okay, 2, and then add it by 1. So which would be 3. You know, which makes sense because it'll take 3 coins to get to amount 3. You know, take this 1 3 times. But then we move on next element array. This is also less than or equal to 3, and then we do 3 minus 3 is equal to 0. Okay, and we already calculated how many coins it will take to get to 0, which is 0 right here. So what we do is 0 plus 1, and which is 1, and since 1 is smaller than 3, we have 1 here. And it makes sense. The smallest number of coins that will take to get to amount 3 will be 3. And we do that for everyone. And eventually, when we reach 7 up here, we can realize, you know, as we iterate through the array, you know, 7 minus 1 is equal to 6. So we take dp of 6 plus 1, plus 1, and then similarly for dp of 3 plus 1, and then dp of 4 plus 1, or sorry, it should be 7 minus 4 and 7 minus 3, okay? Because we know, yeah, it should be minus, and it should be 7 minus 6 plus 1. Why minus? We do 7 minus 3. Why minus? Because we know, okay, to get to 7, we already taken this 3, and 7 minus, so we have 4, amount of 4 left, and we already calculated the dp of 4, so we take dp of 4, which is minimum amount of coins to get to total amount of 4, plus 1, which is the 3 here. Okay, so we're going to get the smallest number of those, and that's how we're going to go about it. So time complexity is going to be O of length coins times amount. And space complexity is going to be O of amount. So now to code this up, what I want to do is initialize my DP array. And initially I'll have everything of float of a value infinity first. And it's going to be of length of amount plus 1, because remember the first value is going to represent a 0. And the 0 and the total amount of coins to add up to amount 0 would be 0, so dp of 0 is going to be 0. And initialize everything to infinity, because remember we want to take the fewest amount of coins to add up to that denomination, or to add up to that amount. So we're going to compare min of dp float in infinity to that amount of coins. Okay, so now for I in range 1 length of dp, we skip the first one because we know it's 0 already. And then for coin in coins, if I minus coin is greater than or equal to 0, okay, what we're going to do, and we do this to make sure, say I is like 4 and coin is 5, how many times can you put 5 cents into 4 cents? That doesn't make any sense. So yeah, we need to make sure if coin is less than or equal to I, which is why I do this. So if I minus coin is greater than or equal to 0, dp of I is going to be equal to min of itself and 1 plus dp I minus coin. This 1 represents the coin that we're taking into account, and this dp I minus coin represents what's left over. So for example, 4 minus 3, where I is 4 and coin is 3, this 3 coin would count as this 1 plus, as this 1, and dp I minus coin would represent the difference, would be 1, and we want to get the minimum number of coins it would take to get to 1 here. So that's what I do. And yeah, that's pretty much it. The code is pretty short. So now what to return? If dp amount is still infinity, that means we have not found a combination of coins to add up to amount, because it's not possible. So return the minus 1, else what we want to do is return dp amount. Okay, so I'll take this for a dry run. I'll use some more examples. Okay, now I'll submit. Okay, great. Thanks for watching.